So I am going to share my screen. Just let me know whether it is visible or not.
Yes, it is visible.
Okay, fine. So this is the Xgslab software, state of the art of the electromagnetic simulation for the power, grounding, and lightning protection systems. So this is the agenda for today's presentation. We will go through one by one. First presentation of about Xgslab, then why Xgslab, then brief introduction and choosing the right module, then a few case studies we will look into, then a product demonstration that will be done by my teammate Harsha, and last QA session. So first of all, I would like to introduce about our company shortly. So our main activities, we specialize in product sales, technical support, training of engineering, software and hardware products as well. So along with the engineering design and consulting services also we are providing. So this engineering markets and supports a range of power system design, analysis software and has an exclusive agency rights in India, Australia, New Zealand or Asia Pacific region for Xgslab, Substation Design Suite, NAPLAN, Power System Analysis Software, Niara, Powerline Design Pro, then Engineering Base and CAR. And this is the Synth Ingegneria, who is our partner and strongly bonded with us. This is an Italian independent company and has been in the field of engineering design since 1993. And the next is Xgslab history. So the evolution of this Xgslab since 1995 till date. So we could see here, this is a GSA from GSA till Shield module. So there are different modules we have introduced in our Xgslab software. Then Xgslab. So shortly Xgs, which is today's one of the most powerful software in both frequency as well as time domain. So it is also useful to protect the human life and installation in the sense like a pipeline, telecommunication network or building. But the application ranges is so wide than we discover, which is unexpected utilization, we could say. Then the modules for Xgslab, which is a GSA, GSA FD, Xgsa FD, TD, which are based on this physics theories, as we know, Maxwell equations, green functions, Sommerfeld integral, Fourier transform, as well as this full wave partial element equivalent circuit methods. Also the module nets, which is based on the theory we can call as a Kirchhoff's law, and as well as the nodal analysis and phase components methods. We are quite aware about these theories as well. So the XGS essentially can be used in the calculation of. So we can do grounding systems, then cathodic protection systems, electromagnetic fields, electromagnetic interferences, fault current distribution, and lightning protection systems. So auxiliary module, we can say. So here SRA, soil resistivity analysis. So this SRA module can find the multi-layer soil parameters, and which is starting on the resistivity measurements and the value and which support both the Werner and Schlumberger methods. Also the next module, which is a Fourier analysis. This module, the module XGS-TD, which includes this FA modules, which allows to move from the time to frequency domain and vice versa. Then the next, this is the basic module of the Xgslab, grounding system analysis, GSA, which is based on the PEC, as earlier said, this method. So this numerical model and whatever may be the equipotential condition of the electrode, that has to be considered under this GSA model, which can analyze the low frequency performance of the grounding system composed by many distinct electrodes of any shape, but with the limited size into uniform or multi-layer soil model. As this is the basic module, so the applications are soil resistivity analysis, grounding system analysis. The next, which is a GSA FD, grounding system analysis in the frequency domain, which is based on a PEC full wave numerical model and which consider the effect of both self as well as mutual impedances of electrodes. So this can analyze the performance of the grounding system composed by many distinct electrodes of any shape, any size into a uniform or multi-layer or multi-zone soil model, and in a frequency ranges we can say up to 100 megahertz. So the applications are wide, like a soil resistivity analysis, grounding system analysis, cathodic protection system design, electromagnetic interferences between underground system, magnetic field produced by underground systems. The next module, which is the XGSAB, so we can call as a over as well as underground system analysis in frequency domain, and it is based on the same PEC full wave numerical model. So model of GSAFD but extended to aerial system. This model belongs. So it can analyze the performance of the system composed by many distinct electrodes of any shape, any size, but above a uniform or multi-layer or multi-zone soil model. So the applications are soil resistivity analysis, grounding system analysis, aerial system analysis, electromagnetic interferences, magnetic and electric fields. Now next, which is a TD, time domain, overhead and underground system analysis. So this is also based on same PEC full wave method. So, but extended to time domain. So it can analyze the performance of the system energized with transient. So the maximum frequency spectrum we can say is 100 megahertz, and this can be used for the switching transient lightning, also in a fault transient in GIS. So the applications are electromagnetic interferences, magnetic and electric fields. So the next module, which is a network solver, NETS, based on the PCM numerical model. So this net model, which is a very flexible tool, able to solve the multi-conductor, multi-phase network in full mesh condition. So for this NETS model, we need to consider the neutral conductor's path as well as the earth path, which calculates the line, cables, transformer parameter, whatever may be the data sheet provided, and the applications are fault current distribution and split factor mainly. So why we have adopted this NETS? So the simulation of this grounding system requires the knowledge of this green layout, soil model and current to the earth. So if there is a current, there is a substantial different current to the earth, that may lead into a fault current. So inaccurate calculation of this current to the earth may lead to the economy in the grounding system sizing. So wrong current to the earth may lead to oversize and unsafe system as well. So for that matter, the net can calculate in a very accurate way the fault current distribution and the split factor or the actual value of current to the earth. So that's why we have adopted this network solver. Now the shield. This is a good and beautiful model we have adopted and introduced, which is a 3D graphical application for the evaluation of the protection of the structure from the direct lightning stroke using the rolling sphere and Ericsson. So we have adopted these two methods, rolling sphere and Ericsson method, which is a worldwide adopted method. So this is the advanced rolling sphere method images with the arbitrary LPS and non-flat ground. So here, as we know, this Xgslab includes the module shield, which is a powerful tool, we can say, based on the rolling sphere method and the Ericsson method, which consider the vertical lightning stroke as well as the flat ground. So this is the images we can see for this rolling sphere radius 25 meter, the protected volume. Now the data input required in Xgslab software. So there are different inputs required like reference standards, soil data, layout data and electrical data. So one by one we will see. So reference standards. So as we know, we are dealing with the different projects. So worldwide standards like European standards, USA standards and IEC standard. So most of the countries adopted these standards. So we have included in our Xgslab software. Then soil data. So as per soil data concern, there are a different soil model like a uniform soil model, multi-layer soil model, multi-zone and presence of thin surface material layer. So this soil model, how we can measure? So we have adopted two methods. First one is a Werner method, second one is a Schlumberger method. So we will see in next slides about more about these methods. So Werner method. So 4-pin method we have adopted. You can see the figure of this 4-pin method and we have already done this calculation So such a calculus part for the measurement of the resistivity, by considering all the parameters, we can calculate the resistivity resistance measurement of the soil. As well as this is a Schlumberger 4-pin method. The same case we have applied with a different calculations. We can calculate the resistivity. Then uniform soil model. So under this uniform soil model, which should be used only when there is a moderate variation in apparent major resistivity or at a high frequency. At a low frequency, the majority of the soil, this assumption which is not a valid. So here we can see the resistivity of a uniform soil model. Further, we can see the graph in detail. Here is a multi-layer soil model structure. So in that, this is a general structure which changes in both vertical as well as the horizontal direction. So vertical changes are usually predominant over the horizontal one, but it is essential to consider the system size as well. So in that case, for the small grounding system, like up to 100 meter, the soil model, which is not a significant affected by horizontal one. But in a soil resistivity, usually a multi-layer soil model, which is appropriate. So it is depends on the number of layers. If a more number of layers, your precision will be good. Then this figure which represent the major resistivity. So here you can see the different layers. So this is first, second, third, fourth. Likewise, we can consider the layers. So this is a 5-layer systems soil model. And here you can see the resistivity and depth graph. And in case of the grounding system, like intermediate size 100 to 1000 meter, this soil model which is affected by both horizontal as well as the vertical changing. So this is the most important and practical case we can say, which is adoptable. Then next, this figure also represents the true double layer soil model case, we can say. So same calculation. So soil model, whatever may be the multi-layer soil model, we can improve this precision in calculation as well. Now the next one, which is a multi-zone soil model, in that we can see here there are different zones. So the multi-zone soil model which should be used when the size of the conductors is so large than the horizontal soil resistivity, which is expected. So in this case, the soil can be assumed divided in more different zones. So each zone, for each zone, there is a condition like a uniform soil model can be adopted. Then only we can adopt this multi-zone soil model condition. So in this case, there are two conditions we can say. More than two zones and buried and bare conductors are there, then multi-zone soil model which allows an approximate solution with a good precision. So in a particular, we can apply if the zone sizes are larger than some 100 meters. And the second one, if the conductors line up too close to the intersection between more zones. So we need to consider these two conditions, then only we can apply. Then the soil covering layer. So last, this is a thin surface material layer up to the 0.15 meter. So here we need to consider the reduction factor of the touch and step voltages due to the superficial thin layer. We can calculate so with a different formulae we have adopted, and accordingly we can calculate this by knowing the thickness and resistivity. And we can show on a figure also. Now the next part, the main part is a layout. Then under that layout, we should know the conductor networks, underground systems, overhead systems, electrodes, span, and elements. Now I can sum up all the features about the Xgslab, like it's a second to none, user-friendly, easy to implement, extensively powerful algorithm we have used, which supports import-export of earth grids into AutoCAD format, as well as the CAD tools available within the software to draw the grids. It is also capable of importing the projects from other software as well, and we can analyze for the better result. Mainly, this is extremely cost effective. We have adopted all three types of worldwide standards. Also, it is suggested by ABB, and it is also by the national green owner of Italy, Terna, as our partners are from Italy. Then as well as it is the best seller in Germany, Italy, Austria, Australia, and many other countries in Europe. As well as we can say South America, Colombia, Bolivia, also adopted by elite groups like ABB, Alstom, General Electric, Siemens, and many international universities across the globe. So there are a big reach, we could say, worldwide about this software. So few features we have recently added, like a seasonal analyzer tool that allows to consider the soil model variation depending on the temperature expected for the location. So this is a also wonderful tool we have added wherever required. Again, we have done the interesting speed test as this calculation of the step voltage, which is a possible from the steps point 25 meter long, and we found there is a fastest computer program response. Also, we have introduced the graphic based OpenGL. So according to that, this 3D vector graphic based OpenGL, the industry standard for the high performance 3D vector, whichever the graphic used in the field of CAD, virtual reality, and scientific visualization and flight simulation, which is a possible. And again, one more wonderful feature, Google Earth export. So in case of the last system, we can see the result in real world. And it is useful to see the touch and step voltages of a transfer or induced potential superimposed to the local detail map. So we have recently introduced this feature as well in our Xgslab software. So we will see with more details for the case studies like high voltage substation grounding, distribution system, solar PV power plant, low frequency induction study, LFI study, rail system, and industrial plant. And we have dealt with all these projects. So let's say substation. So case one, which is we have considered 132 kV voltage, fault current 21 kiloampere, fault time 0.5 second, European standards with a double layer soil model. So here we can see this is the double layer soil model, and the legends, which legends shows the different measured value, calculated value, as well as the whatever may be the RMS error and resistivity values we can see over here. So for the same substation, the general layout we can differentiate with a different color codes. Then leakage current distribution also we can show with here you can see the legends with a different color codes, the actual range of this electric field, the maximum minimum range also we can define. Then longitudinal current distribution in a similar way. Potential distribution, earth surface potential distribution. In a good way we can show. Then touch and step voltages with and without gravel. Here we have considered 5 by 5 meter. Then cathodic protection. Now general layout which includes the anodic beds. For this, this is all related with the cathodic protection system where CP is required. Then leakage current distribution. Then potential distribution. Then potential distribution in a pipe on a pipeline to be protected. How we can do the simulation in our Xgslab software in a new general layout with a multi-zone soil model including anodic beds. Now the next case study we can say the industrial plant. So having 230 kV voltage range, 40 kiloampere, 0.5 second IEEE standard with a double layer soil model. Here we have adopted. In a similar way, we can do here the general layout for this particular industrial plant. Then leakage current distribution. Then longitudinal current distribution. Then substation potential distribution for this industrial plant. Then earth surface potential distribution. Touch and step voltages with and without gravel. Here we have considered 3 by 3 meter. Leakage current distribution. Longitudinal current distribution. Potential earth surface potential distribution in a different way. And touch and step voltages with without gravel 10 by 10 meter. Here we have considered Now the photovoltaic plus wind power plant. So it's a like a double layer soil model. Here we have considered. So green general layout in a similar way for this plant. Then leakage current distribution. Then longitudinal current distribution. Then potential distribution. Then earth surface potential distribution. Then touch and step voltages without gravel 5 by 5. Here we have considered. Then gravel with without gravel with 2 meter. And next one, which is a tower earthing concept. Here also we have considered how it is used by considering this average tower resistance, span length, earth wire. So here this is the foundations of this tower earthing. Here we can see the top view, that which is the old method, we can say, with this 3D view by considering this earth tower resistance and current. So the traditional solution we can see. Then touch and step voltages for this tower earthing. Then innovation solution. This is a different view than this traditional one by considering the values of this earth resistance and earth current. Innovative solution, how it is a different than the traditional one, we can compare later. Touch and step voltages. Then here we conclude with the graph, how traditional and innovative solution touch voltages, the comparison matrix. Then comparison graph, we can say the step voltages. For the step voltages also we have defined. So for the electromagnetic fields now, for the substation, so longitudinal current distribution, then magnetic field mainly, as we are focusing on a magnetic field. So magnetic field in the range of 3 to 10 micron also here we have considered for the particular substation. Then safe areas also we can define with the different color codes. You can see the legends. So with the legends, we can show the magnetic field safe areas, potential distribution, then electric field also we can show. Then electric field in the range of 3 to 10 kV per meter. Then interferences. Apart from the field, there is interferences also. So for that matter also, here we have considered for that particular substation. Here we have taken example. The potential distribution in a normal condition, their maximum minimum limit for the safety point of view, the corrosion point of view also here we have considered. Then calculation, consider the contemporary conductive and inductive effects as well. The maximum minimum limit of this voltage for the safety at that particular substation. In a fault condition means in a complex scenarios, which are also possible if there is. So power lines and pipeline networks with the multi-zone soil model here we have considered. So in a fault condition, one considers a power line at a time. So that is also the good thing for this we can do with the complex scenarios. And the hydropower plant. So for the hydropower plant also here we have considered the underground power station pipe flow type. So single phase to earth fault current, which is a 300 ampere, here we have considered. Then underground power station, that intake here we have taken. Then a power plant chamber. Then leakage current densities also we can show. Then the potential distribution that results for that particular hydropower plant in earth surface potential. So this is all about the case studies. So hope you understood all these case studies, which is related with these electrical things and how we have done the simulation in our software. So by visualization, at least I hope you will get the idea. So for more details, I request my teammate Harsha to demonstrate in a quick way. So that would be really easy for you to get the clear idea about the Xgslab software and how it is done in actual software. So Harsha, please share your screen.
Yes, thanks Madhuri for your wonderful presentation. I'm sharing my screen. Please let me know if everyone is able to see my screen. Is my
Yes,
screen visible, Madhuri?
Yes, it
yes,
is
yes.
visible.
Okay. So yeah, so I will just introduce about what we are going to see next. So first of all, we will see the soil resistivity modeling, then ground green design in software, then simulation on solar plant earthing system, then analysis such as earth potential rise, touch voltages, step voltages, and transfer potential, and safe regions analysis. So like my design flow will include the selection of input first. So in that, such as the standard, then electrical parameters such as frequency, fault current, fault clearance time, then generation of soil model. So in the Xgslab we have the three options to for the soil model, that is uniform soil model, multi-layer soil model, and multi-zone soil model. Then next step is to insert the ground grid in the software. So if we can draw the ground grid in software, as well as we can import it from CAD layout, like from DXF format. Then the next step is the calculation and results of all scenarios, and then we can generate the automatic report from Xgslab software. So like without any delay, I will just go into the software. So here you can see this is the interface of Xgslab software. Once we open the software, we can see this. So this here you can see the history of the Xgslab software. If you click on this, you can see the history. Then here you can see which like any new releases there. Or here you can see the information about the Xgslab, like your license, which license you are using, and documents like such as user guide, license condition. Then here you can see some YouTube videos also. This is the Xgslab website. From here you can download the software, and you can download some tutorial examples such as like examples. Then here are some social media updates about the Xgslab software, and here you can download the tutorial documents such as tutorial projects on all modules. So yeah, so this is the interface of Xgslab software. So the interface is really very easy. Actually, the file, windows, and help. So in help section also you can find the tutorial and user guide. So in file you can see this is the start page. Then if you have to create the new project, we have to click on this new, and yeah, again here are also some shortcuts are there, so you can start from here also. So here I'm just clicking on this new project to start. So I will just give a name, just saving it on desktop, and I will give the name for G renewables. Save. So as soon as I created the new project, you can see the changes happen in screen. So here you can see the new tab is generated, that is the project. And here you can see all the modules like GSA, GSAFD, XGSAFD, XGSATD, nets and shield. So this module is like in some cases, like if you have purchased only one module, then only one module will be enabled in the system, and all other modules will be disabled. But we have the full license, that's why all the modules are enabled here. So like again you can see all other steps are grayed out, like disabled. We can't go like one step ahead without completing the first step. So because of this, it is very useful and user friendly, because we can't do the wrong things in the software. And yeah, on the bottom bar also you can see the like quick information about your project, like the current project, like project name. Then this is the symbol for reference standard. Once we choose the reference standard, then it will show which reference standard is chosen, then the frequency, and this is the result scale. And this is the most important and useful feature about the software is hint. So here you can see the choose module. Hint is telling us first step is we have to choose the module. So yeah, I will for my today's demonstration, I am going to choose the module GSA-FD. So as soon as I choose the module, my next next icon are enabled. So here you can see, and here also you can see hint is telling define waveform. So like first, before going to the waveform, I am just putting some here we can put some general information about the project. So here you can see like we can put the project information, like description about the project if you want to put, then date of the project. Then here you can put the company details, for which company you are doing this project. So I will just put some information like G Renewables. Here you can insert that company logo if you want, address and city. Then we can put designer information. So I'm just putting some information here. So I engineering, and here also again you can put the logo and all the details. Here you can put the site details where you are executing this project. So installation of site and city, state, etc., and geographical location of that site. So we can put this information if we have, and we can apply this. Once we apply this, that all information will be like we can see that all information in the report, as well as if you are sharing your project with anyone, that all information will get shared. So that is like useful for everyone to get the info, like quick overview about the project. Then next step is to choose the reference standard. So here you can see various like for various calculations, reference standard options are given. So here first is for touch and step voltages. So here you can see IEEE, IEC and European standards are there. So I'm just choosing the IEEE standard for touch and step voltage calculation. And if we are doing this other calculation like split factor calculation, conductor sizing, then for that also we can choose the various reference standard from the this list. And the next step is after choosing the reference standard, next step is to define the waveform. So here we are just like, as we are in frequency domain, this transient waveform is disabled. So I am just choosing the sinusoidal here, and I will put the I will do the demos like project at power frequency, that is the 50 hertz. So I will apply the frequency here. Yeah. So here I have just applied this frequency, and my next tab is enabled, that is about the soil model modeling. So here you can see that is the three types of soil model we can analyze in Xgslab software. As Madhuri also previously explained about this, all the soil model modeling. So uniform, multi-layer and multi-zone. So actually here you can see the uniform soil model. So in uniform also, if you have the data, you can put directly the data here, the resistivity of with low frequency, then permittivity. And if you don't have this data, you can calculate and you can measure like if we hit this calculate button, then here you can put the information about the the data measured on site, that is the electrode spacing, then electrode spacing between current and voltage probe. This is the resistance and resistivity. So for my today's project, I am just going to choose the multi-layer model. So here I have just chosen the multi-layer model, you can see. So here again there are various types of frequency dependence of this model are given. So independent, Messier, and like there are many. But actually this frequency dependence, if we are doing our calculations on very high frequency, then only these various models will affect. As we are doing the demonstration on high frequency sorry, power frequency project, so I will just choose as independent. And here I can see, you can see the multi-layer model modeling. So if we have the data, like this is my first layer resistivity, second layer resistivity, we can add directly the data here. Like if we add here, then the next row will be added and we can put the data here. But I have some measurements from site, like electrode spacing between the voltage probe and current probe, and the resistance of the soil. So here I'm just calculating my soil model from that data. So if I hit this soil resistivity analysis here, so here you can see this table is, we can see this table, and here you can see the major type, what values we have. Did we have the resistance value or did we have the resistivity value? So I have the resistance value, that's why I have, like, we can check this box, and if we have the resistivity value, we can check this box. And here we can manually add the values if we want, like one by one. So if we click this add button, then other rows will be get added here. But like, as I have the values in Excel, and it is very easy to put the value from Excel in this software, so I'm just copying this value, and here you can see the paste option. So to paste the values, our value should be in this format, like the tag A, C and R. So I don't have the tag values, but A, C and R. So that format is given. So if I check this value here, yeah. So you can see how easily and quickly I have pasted all the values, all the measurements in the software. Actually, like, this values, I have very little value or small values, means less value, less number of measurement, but in many cases the number of measurements are very high, and it is very hard to put all the values one by one. So it is possible, like, it is very easier to paste the values from Excel. So yeah, here I have pasted the value, and here on this graph you can see all the value, like resistivity values are got pasted here, like drawn here, points are drawn. So again, here we can resize this axis if we want, and we can see this graph in log scale also. If I click this log scale and view, so here you can see the log scale. And then automatic, actually the layer numbers, like how many layer model you have to generate from these values, that is Xgslab is asking us. So it is depend on us, like how many layer we want. Otherwise we can directly say this automatic detection, and with the automatic detection, if we hit this calculate button, it will calculate the value, like automatically calculate the layer numbers also, like which layer number we want. So if I hit this calculate, so see, Xgslab automatically developed the 4-layer soil model. So yeah, so here you can see the layer numbers are 4. But if I disable this and I want to choose the 3-layer model, so I will just choose the 3 here and will hit the calculate. So here you can see the software is telling that is the poor number of measurement with different electrode spacing. So actually this is the warning. Actually it is getting, we will get the result, but it is telling like the measurements are less. So here you can see like we have only the 8 measurements with different electrode spacing. So if we want to go with more layer number, that we will require the more more measurements here. So here you can see the 3-layer soil model is generated, and the RMS error is 7.870%. So it is very less as per IEEE 80 standard. 10% of RMS error is accepted. So 7.87 is okay. So I will just apply I can just apply this, and here you can see the table for soil model. Like first layer, resistivity of my first layer is 44.62, resistivity of second layer is 566.43, and resistivity of third layer is this 2173. And these are the thickness of layers. So first layer thickness is 0.83 meter, then second layer thickness is 35.66 meter, and third layer thickness is infinite. So again, here you can see this soil covering layer, if you want to like increase the resistivity of any surface or any special, then if we want to add some covering of resistive element, like resistive material there, so we can choose that covering also here. So here I'm just choosing the gravel with 3000 ohm meter resistivity with the thickness of 300 mm. So then we will just view this model. So here you can see this is the like soil covering material I have added. So this is that resistivity showing here, and these are the 3-layer model, like first, second and third. So we can see this model. So here there are various options. If we want to save this graph, we can save it from here. If we want to print, copy and snap. If we click on this snap button, that this graph will automatically copied in our report, like automatic report that will get generated from the software. So if we want to add the caption, like here we can see the soil model, but if you want to give the detailed name for this graph, so we can give it. If we want to add some description, we can add it here. So yeah. As like now we can see our soil model is got generated, and next step is to here we can see data import, like we can import the data grid layout from the DXF format, or we can draw it in Xgslab software. So first of all, I will just click on this draw button. So here I have just click on this draw button. So here you can see various symbols are there, like horizontal conductor, then ortho horizontal conductor, vertical conductor, circular circle, or this is the rectangle. So these are the various options are given here to draw the layout in software. And this if you click on this question mark, it will show you the use of your keyboard button to draw the symbol, like draw the grid. So like if you want to snap at endpoint of any element, then we have to press the shift button. Then if you want to snap at midpoint, then we have to press control button, like etc. So I will just say okay here, and we will I will just show you how easily we can draw a grid in Xgslab software. So I'm just choosing actually before choosing the conductor, before choosing this draw options, we have to add which conductor we have to draw with. So this is the electrode, like in which electrode we have to draw. So I will just say electrode 1, then I will give the name tag as a grid, and then we have to choose the live conductor from the library. So I will say the conductor. So here in library, 3 types of conductors are available, that is stranded, solid and pipe. So I will just say the stranded conductor, and then we have to choose the description, like which conductor we have to use. Here various types of conductors are there, so I will just say 10 square conductor I am using. This Z will define the drawing depth, the on which depth you are going to draw your earth grid. So I will just say 0.5 meter below the ground. So this is my drawing depth where I am drawing my layout. So then again, if we are drawing any horizontal conductor, we can define the length here if we want. And this is the if we are drawing any vertical conductor, we can define the length here like that. So I will go up, and now I will just click on this rectangle button. So here on this bottom bar, you can see the messages. We are getting the messages of your all operation, what we are doing. So here we can see the multi-layer soil model is applied. Then I have just chosen this rectangle. No? So it is telling like in which format we have to put the value. Like we can draw it easily like this, but you can see like we don't know the length, what length we have drawn here. So if we want to draw any specific length, height thing, so we can just draw with the this coordinate. So I will delete this first, and I will choose this rectangle, and I will put the values like x coordinate. I want to put as like x coordinate is 0, then y coordinate is also 0, z coordinate is 0.5, then length I will say 100, width also I will say 100, and at an angle of 0. So yeah, now you can see how easily the rectangle has drawn. Then if I want to make it as a grid, so I will just click on this conductor and I will say array. I want to array this conductor. So yeah, with the 10 meter of spacing, so I will just say 10 and sorry, not this one. I'm doing okay, y. So I will say I have to increase this to 10 and will increase this. So 10, and here I will say minus 10. So you can see on like on this negative side, all the lines will get drawn as applied. So here you can see all the lines got drawn. So as in the same way, if I want to array this conductor, I will go here and we'll see I want to array this conductor. So on x axis, we'll just say 10 and 20. So you can see how easily the grid has drawn. Then if I want to add some vertical rod on the corners or anywhere, so I will just press the shift key from my computer keyboard, and yes, if I want to draw the vertical, so here I am just choosing the length of vertical conductor is 3 meter. So yeah, it will automatically it will automatically draw the vertical conductor of it will automatically draw vertical conductor of 3 meter length. So I will just say the tag for that is rod, and all the things like conductors and all the things will become same. So choosing the vertical conductor, and now I will press the shift key and you can see it is snapping here. So yeah, in the same way I will draw all the rods on all corners. Yeah. So here in 3D we can see this layout. So as per this here on the corner you can see the rods. So those rods are 3 meter, length of those rod is 3 meter. That's why it's looking very small, but it is drawn here. So in this way we can draw any grid in Xgslab software. So now I will delete this everything and I will tell you how easily we can import the layout from the DXF format. So here you can see this is the solar plant layout drawn in like earthing layout for solar plant drawn in AutoCAD format. So here you can see it is drawn in various layers, that is AC rods, boundary converter, DC rod, and then substation earthing like EHV, etc. So now I will go to software and we will import that layout in our Xgslab software. So here I'm clicking on this import and export. So you can then we have to select the file where it is. So here on I will go to solar plant earthing and here is my layout. So just open that. Then we will add all the layers one by one. So I will add my first layer, that is the AC rods and electrode. Actually this electrode numbers are depends on if your all the earthing grid is connected to each other, then we can say all the electrode numbers are same. But if you are doing like some things are not connected, one is like far away from other and it is not connected, so in that case you can give different electrode number. And here we are just choosing the conductor from the library, which conductor we have to use. So solid, and yeah, so this Z is vertical shifting. Like if your CAD, if your grid is drawn in CAD layout in at Z equal to 0, and you want to shift that in soil like some meter in some depth or some meter below the ground, so in that case we have to use this vertical shifting factor here. But I have drawn this layout in CAD in Z equal to 0.5 meter, so I will not use any vertical shifting factor here, and will apply this. So in the same way, we can add all other layers. So background means it is just civil entities. So it will not take the part in calculation. So here you can see I have chosen the layer background, and here I will enable this. So we can see that, but it will not take part in calculation. Then third layer is converter. Electrode number is again 1. Apply. I will add another layer, that is the DC rod 1. Apply. EHV. So I have added all the layers here, and this scale we have to choose like on which in which scale we have drawn our layout in CAD format, like in DXF. So here actually my layout is already drawn at 1 meter equal to 1 CAD unit. So but if your layout is drawn in different format, like in different units, so here various units are given, we can choose any unit from here. And now like everything is set, I will just click on this import. So here you can see I have imported all the elements and all the conductors in the software. So here you can see list of all the conductors, like the length of that conduct element, and Z starting point, X starting point, X ending point, Y starting point, Y ending point. Then length of each element on each conductor, and like library, like type of conductor, which type you have chosen, description for that conductor, then everything. So this all the things are get automatically imported in the software. So now we can see how the layouts. If you go to here, so here you can see the layout. It is just imported as it is in AutoCAD. So so if I click on this background and view 2D, so now you can see the background also that is there in AutoCAD. So yeah, so now you can see like we have imported the layout. So next step is like as we are doing the earthing, so we have to create some fault in the on the layout to study the earthing. So here like on high voltage side, I will just click here on substation side, and we'll see the conductor editor window will open. So in conductor editor window, we have to go to victim, and this is the starting point injected current. So we can inject the current, like fault current here, like how much of fault current we want to give. So for this I will just say I have to create the fault of 6 kiloampere. So here again, if you want to create that fault at starting point or ending point, so that also we can choose from here. So I will just say at starting point and will apply. So here you can see on this conductor that fault is get created. So after that, next steps are to set the limits for touch and step voltages. So here as we have chosen this IEEE 80 standard, so like all the limits will get calculated with reference to this standard. But if we want, we have some user defined value that we want to put for touch and step voltages limit, so we can directly put the values here. So like for this project, I'm just going to calculate with IEEE 80 standard. So as I hit this IEEE 80 standard, so this is some input we will require. That is the fault clearance time. So I will just say it's 0.3 second. Fault clearance time is 0.3 second. And this is the body resistance, then body weight. And if the person, like maintenance person, is wearing some shoe or glove, so if we want to put that resistance, we can put that also here. But right now I'm just leaving it blank and we'll calculate. So here you can see the touch and step voltages limit are got calculated. So here you can, this is the current flowing through the human body, then permissible touch voltage limit, then this is the permissible step voltage limit, then this is the permissible touch voltage with soil superficial layer, that is we have added the soil covering layer. So with the inclusion of this soil covering layer, our touch and step voltages, permissible touch and step voltages will increase and will apply. Here you can see all the legends, like this is the time, that is fault clearance time, then touch potential, step potential, then sorry, permissible touch potential, permissible step potential, and with soil covering layer also. So I will just apply this and we'll snap this image for our report purpose. See, so as I have applied here, so the next step is to debug, like we have to check is there any error in our calculation. So I will just hit this debug here. So here you can see I'm getting the debug is successful and hint is saying we are ready for calculation, means there are no error in our design. So I will hit this calculate button here. So yeah, as if like as the calculations done, it is showing, hint is showing result available, and here you can see one new tab is added, that is analysis, and we can see the results here. So like first we have done the earthing design. So first step is to get the earthing impedance. What will be the earthing impedance? So here you can see, we can see the ground potential rise and earthing impedance. So with reference to fault location. So here we can see the reference point is fault location point. So if we want to rename this, we can rename it here. So I will say fault location point is my reference point. And we can see here, this is the potential modulus, that is the earth potential modulus. Then this is the earthing impedance. So this earthing impedance we are getting, that is 2.808. And this is the earthing impedance phase, if you want to check. So yeah, x coordinate and y coordinate, z coordinates we can see. And if we want to check with respect to any other point, then so in data section, if we go to view 2D, so if we want to see any thing like with respect to any other point, if here is something I want to check what will be the potential at this point with reference to fault location. So here you can see we can set the reference at any location that we want. So as if we can set the reference here, and I will just say reference point 1. Okay. So like with the reference to this fault location, we can see the result. think we have to put it again. So here now you can see it's got added, that is the reference point. So with this with that reference point, this will be the potential modulus and this will be the earthing impedance. So next step is to in analysis. Next we can see the line calculations and area. Before that there is a distribution of we can see. So here various types of distribution are given in the software, like leakage current, superficial, potential, then current distribution, electromotive force, covering stress voltage, various types of distribution. So like I will just click on the potential distribution here and we'll see, we say view 1D. So here we can view 1D of the potential distribution. So if we want to want to see at any specific point, suppose this is the maximum potential distribution I am getting and I want to like highlight this part. So I will just click here and I will say max. So here that table is got added. So and it can be used in report. So that got added there. So again we can export these values in CSV format, like CSV format, and we can get the all the data in Excel also at all point. We can view 2D also. So in the 2D potential distribution, we can see the ranges of the this color, every color range is given here. So with the reference to this, we can see what will be the potential distribution at any point. So yeah, you can see, and again by clicking on this graph also, we can see. So as like I have clicked first here and then here. So here like then we can get the potential difference between the 2 point here. Again so this is the potential distribution. If again various types of, if we want to see for any specific layer, then we can select that layer only and we can see the potential distribution for that specific layer. If we want to see for any specific conductors, then from which conductor to which conductor we want to see, we can choose here. If we want to set some limits, like I want the potential distribution from this to this, so it will show like which is going above your limits, so we can set the limits here. We can see the modulus and real part and imaginary part of potential distribution again if you want to see in 1D. So previously our like we are able to see only one graph, so now you can see there are two graphs, three graphs here. So imaginary, real and modulus, three we can see. So that can also be seen. And next step is to calculate the touch and step voltages. So as I click on this line calculation, so there are two types of calculations are available in touch and step voltages. That is the line calculation and area calculation. So actually in area calculation we get the very detailed overview about the everything. So if we want to like something is here, some fence or any metallic structure, and we want to see what will be the touch and step voltages at that point, so we can just draw the line there. So here we can see the draw symbol here anywhere, like we can draw and we can hit this calculate. So if you want to see the line calculation along this line, so here various reference point, like we have to select the reference mode with the reference to what we have to see. So I will say the reference point and my fault location point will be my reference point will be. So this will be the potential at that line, we can see. Touch and step potential. So now we will go to the area calculation. And in area calculation, we have to draw the area where we want to see our result. So I will just draw like here the whole area and we'll hit the calculate. Like area calculation will be ready. So here you can see the earth potential, touch and step voltages result we will get here. So first of all, we will see the earth potential in 2D. So here we can see the earth potential in 2D and the values are given here. So ranges for all the things, like all elements are given here. So maximum range of earth potential and minimum range of earth potential is also given here. Then here again we can set the reference point, like on with the reference to what we have to see the touch and step voltages. So I will just say I have to see with reference to my fault location point. So I have just created reference point and fault location, and I will go here and now we will see the touch voltages. So this is the 2D view of all touch voltages we are getting. So here in the legends we can see the ranges of color, and if we want to here we can see the maximum and minimum touch voltages. Then again, if you want to view this result in 3D, can also, yeah. So this is the 3D view. In 3D, like we will get a very clear idea about everything. So this is the ranges we can see, and this is the graph. So this is for touch voltages. Then we can see the step voltages also. So this is the graph for step voltages we are getting. You can see 3D also. So this is the graph for 3D step voltages, and here are the ranges given. Then here for earth potential, this Xgl viewer option is given. So this is the actually we can view our layout in all the format. So here you can see the like we can view the rotating view. We can see the rotating view of results. Here like various options are given. If we want to change the background, we can change. If we want to take a snip at any specific point, so we can capture image at that point. And like various options are given, like which view you want to see, top view, side view. So various options are given. So this is again a very useful feature for Xgslab. Then like we have seen the touch and step voltages. Now we have to see the safe region with respect to our touch and step voltages permissible limits. So here we can see the safe area option. So if I click on this 2D, so we can see this some of the regions is like yellow, and some regions at some corner is red. So like the meaning of this, it is explained here. So if the touch voltage is less than permissible, in this case green means touch voltage is less than permissible touch voltage, and step voltage is less than permissible step voltage, means that area is safe. If the touch voltage is greater than permissible touch voltage, and step voltage is less than permissible step voltage, means that area is yellow, and this means that area is safe for step voltage but not safe for touch voltage, and this red means it is not safe for touch as well as step voltages. So here we can see the safe area. So this safe area we can see without the soil covering layer. So only few part here is green, otherwise everything is like not safe for the step voltages. So here we can hit this, we can add the soil covering layer. We have already added in our calculation, but with the soil covering layer we can see the result for safe area. So here with the soil covering layer, we can see our safe area got increased. And now it is depend on us what the safety measures we have to what the how we have to increase our grid. Maybe we can add some extra rod, or we can Like we can add soil covering material. So it depends on engineer what the solution they want to provide. Again, this we have seen with respect to reference point. Again, there is an option to see with respect to all elements and what the reach is, like how much meters of reach distance we have to see. So I will say, like I want to see the result with respect to my all elements within the reach distance of 10 meter. So here I can select the 10 and now we will view the result. So now you can see with respect to all element, the result of touch and step voltages and everything. It is the result of safe area. We can view that result for touch and step voltages also if we want. So this is the with respect to all element with the reach distance of 10 meter, the result for touch voltages. And for step voltages also we can get this result. Yeah. So again, this is one important feature I forgot, like the XML, like we can export this data in the Google Earth. So that is again a very useful feature for a large site or large scale. So this all about the software. Now we will go to the summary table and we will view the report. So here, like it is asking which waveform or which part of the report you want to see. So I have selected all the, like tick the all the elements here. I will say select all and will apply. Now we can see the results like report. So here we can get the idea about our project. So which module we have selected, then general information that we have placed in project information, then which waveform we have selected, the soil cover soil model modeling, like the measured values, then layers, calculated layers, then soil covering layer we have used, then all the graphs that we have snapped, then this is the layout, like means fault current, what fault current we have given, then limit for touch and step voltages, then these are from here we can see the result. So results are for GPR and earthing impedance. Additional impedances we haven't added, that's why this table is blank, and all the results that we have snapped. Yeah, so this is all about result. Here we can see the we can get the list of item, like which item we are using. So this is easy, like it is easy to prepare the bill of material. It is telling us the length, thickness of all the conductors, how much of length the conductor we want, what will be the thickness and everything. So again, if we want, we can export this report in document format and we can edit it as per our requirement. So that's it from our side. So if you have any questions, feel free to ask. Thank you.